Now we'll study about Biot-Savert's law. This famous two scientists, Jean-Baptiste Biot and another scientist Felix Savert. So combining the combined law, a very famous law, which is called Biot-Savert's law. Actually, this is very important law for magnetic induction process. So before that, we have studied about the magnetic, what is magnetic field and magnetic induction also. Then we can describe this law. Hello. So Biot-Savert's law is an equation describing the magnetic field generated by a constant electric current. It relates the magnetic field to the magnitudes, direction, length, and proximity of the electric current. And the Biot-Savert's law states how the value of the magnetic field at a specific point in space from one short segment of current carrying conductor depends on each factor that influence the field. So now we'll try to states and describe the Biot-Savert's law. Now the statement of Biot-Savert's law. This, we can state the statement. The statement of Biot-Savert's law. The law states that the magnetic field along a vertical current carrying conductor or wire in a closed surface is directly proportional to the current I and inversely inverse proportional to the perpendicular distance distance from the point or wire or conductor. That means if we take anywhere like this, then if there is a circular air. Suppose this is the direction, electricity direction I, and this is the dB. This is the radius R. And here is a small length. This is the DL. Small length DL. And this is the midpoint of this small length. This is the small length. This is the midpoint. Okay. And this is the angle theta. This is the direction I. And here this is the tangent. Okay. Tangent. So this can be written as dB is proportional to I dl sin theta by r square, or dB equals to mu naught divided by 4 pi. This is the proportionality constant, which is equal to 4 into 10 to the minus 7. We have already known about this. I dl sin theta by r square. So this is the actual statement of Biot-Savert's law. And sin theta is the angle between the electric current and the distance between the magnetic field and the midpoints of the DL. Okay, this is the sin theta, and this is the statement. We can find out the total B by integrating on both sides. We get the total magnetic field by integrating on both sides. The magnetic field dB at any point due to the current element is given by the Biot-Savert's law. Thus, if DL be a line element of a conductor carrying the current I, then at point P, this is the point P. This will be the point, any point P. P, dB is the magnetic magnetic field. So, and its magnitude is given by this formula, where R is the position vector from the element DL to P. Okay, from DL to P. This is the R element. Okay, this is the magnitudes R, and theta be the angle between R and DL. R and DL. Okay, theta be the angle between R and DL. So DL length will be this. This is the DL length. Okay, R and DL. And the quantity epsilon by 4 pi equals to 10 to the power minus 7. This 4 pi equals to 10 to the power minus 7 Newton per ampere meter. Okay, and this equals to 10 to the power minus 7. We have to remind this. Now we'll discuss the application of Biot-Savert's law. Application of Biot-Savert's law. Application. Okay. Application of Biot-Savert's. Application of Biot-Savert's law. The application of Biot-Savart law. So we discuss the application. There are many applications of Biot-Savert's law. First application will be find the magnetic field, magnetic field due to a long wire. Okay, due to a long wire. To find the so for this we can draw a figure for that. Now we are trying to find out the magnetic field of a long wire. Okay, so this is the long wire, and this is the x-axis. This is the I unit, and this is the Z unit. This is a long wire. Suppose at a point P, we have to find out the point P. This is the Z vector along y-axis, and this is the I unit vector, and this is the R vector, and this distance is capital R, and this angle will be theta minus 90 degree. And this is the angle theta. Okay, and this will be what? Phi minus theta angle, and this length y length, and I electricity is passing through this conductor. So this is the radius R. So from the figure, actually, if we take the small length, for a small length dy along y-axis, we get I dy equals to zi dy. Because I is the electric current along dy, Uh, so by so by Biot-Savert's law, by Biot-Savert's law, we get magnetic field at point P, magnetic field, the magnitudes of magnetic field at P equals to mu naught by 4 pi I dy z cross r divided by r square. This is the vector product. So along the y-axis, the unit vector is z, and r is the another unit vector r. So we can write here, or dB equals to mu naught by 4 pi I dy sin theta by r square. Now to find out the whole magnetic field, we have to integrate on both sides up to minus infinity to plus infinity 4 pi I. So this integration will be minus infinity to plus infinity. Here minus infinity to plus infinity length of air along the y-axis. So we get I sin theta dy by r square. Since r, l, and theta are the related to each other, so we get sin theta equals to, here sin theta equals to, we can write sin theta equals to sin pi minus theta, sin pi minus theta in same quadrant, and positive for sin, and this equals to capital R by small r. Okay, because perpendicular by hypotenuse, sin equals to perpendicular by hypotenuse. So r equals to, therefore small r equals to capital R cosec theta, small r cosec theta, and y equals to minus r cot theta. Again, tan theta equals to what? Tan theta. This is the calculation. Tan theta equals to capital R by y, or tan pi minus theta equals to capital R by y. Therefore, y equals to minus r cot theta. And dy equals to, what will be for this? Dy equals to minus r, sorry, plus r cosec square theta, plus r cosec square theta. Just by differentiating on both sides. So now from here we get magnetic field, total magnetic field B equals to mu naught by 4 pi I. Integration will be changed 0 to pi, 0 to pi. So and this will be d theta. Okay, that means y transform to theta. This is why we get sin theta, and dy equals to what? R cosec square theta, r cosec square theta, and sin theta. R square means what? R square cosec square theta, d theta. So from here we get B equals to mu naught I 4 pi mu naught. So mu naught equals mu naught I, and these are will be cancelled from each other. So capital R will be the constant and 0 to pi only sine theta d theta. So from here we get actually only after integration we get only 2. This is why b equals to can be written as mu naught I divided by twice pi r. Only this value will be only 2. So this is the actually application of Biot-Savart's law for finding the magnetic field due to a long state wire carrying a current. So I hope very easy for you. So we studied about the Biot-Savart's law, and we also discussed the application of Biot-Savart's law. So actually this quantitative role for the computing magnetic field from any electric current, we have to choose a differential element of wire length dl and the carrying current is E. So the field dB from the element dl at a point located by the vector r is given by the Biot-Savart law. Okay, and this permeability constant mu naught 4 pi multiply 10 to the minus 7 Tesla meter per ampere. So if we this Biot-Savart's law, uh, an infinitely long state wire carries electric current I. If, then determine the magnetic field generated at a point located at a perpendicular distance r from the wire. So we have derived it. Choose an element ds or dl, anyone you can choose. The Biot-Savart's law. By Biot-Savart law, we can find out the dB point. Okay, so this is the application we have used. We can use this method also. Okay, this method also. Now we can solve some practical example by using Biot-Savart's law. A power line carries a current of air. Carries current of air. So a power line carries. We can just using this one. This is the application I have uh, proved. Application of Biot-Savart's law for a long wire. Field of a straight wire actually. Okay. We can use this method. Just we have proved mu naught I divided by twice pi r. We use this method also. And a practical matter, suppose a power line carries a current of 500 ampere. What is the magnetic field in a house located 100 meter away from the power line? So actually, which one we have to use? Obviously, this is the we have to use Biot-Savart's law for finding this one. Here, the magnetic field is actually 100 meter away from the long wire carrying and 10 centimeter. But here 500 ampere and the long distance is 100. So we have to use the capital B equals to mu naught I divided by twice pi r. And this just putting this is the mu naught is the permeability constant 4.2 10 to the power minus 7 minus 7 Tesla meter per ampere. So this one So this one will only 1 micro Tesla. Recall that the Earth's magnetic field is 10 to the power minus 4 Tesla. That means 100 micro Tesla. So for a circular where of radius r carries a current I, another application. What is the magnetic field at the center of the loop? So suppose this is the circular and capital R is the radius, pi is the subtended angle at the center, and small r is the radius distance between center to the circumference, where dl or ds infinitesimal length exists. So what is the magnetic field at the center of the loop? So you must know from the Biot-Savert's law, dB equals to mu naught by 4 pi IDS R, my capital R cube. This is the vector form. Now dB equals to mu naught IDS capital R divided by R cube. Just uh, replacing small r to capital R, we get capital R I R ds equals to ds d pi. Then I d pi by capital R. Then we get, after the integration, we get I d pi means integration total magnetic flux pi. So this is the another application. Now force is between wires. The two where one is I1, another is I2. So if we want to find out the force between two parallel wires, uh, we have to use first of all the magnetic field for the first wire V1 equals to mu naught I1 2 pi a, and force on the second wire due to the field. So force will be where 2 due to the field 1 will be L I2 V1. You must know from our previous slide force equals to ILB. Okay, so just putting the values of B1, we get mu naught L I1 I2 divided by twice pi. So for forces between two parallel wires, we have to use this one. Now, magnetic field exerted forces on moving charge. So dipole moment create electric current produces magnetic field. You must know about this. And where carrying current produces forces on each other. So this is the actually application of Biot-Savert's law, and we have discussed also in our slide. So the Maxwell's equations in differential form, there are 4 equations. That means 4 basic laws of electricity and magnetism. These 4 laws are Gauss law of electrostatics, first one. Second one, Gauss law in magnetostatics. Third one, Faraday's law of electromagnetic induction. And number 4, Ampere's law with Maxwell's correction. All these 4 Maxwell's equations along with their salient features are being discussed here. The Maxwell's first equation, the first equation represents Gauss law in electrostatics. That means divergent of electric field equal to charge density divided by epsilon naught. Okay, this is a time-dependent steady state equation which relates the spatial variation or divergence of an electric field with charge density. This relation is true both stationary and moving charges. And second one, Maxwell's second equation. The second Maxwell's equation represents Gauss law in electrostatics. Mathematically, gradient of magnetic field equals to 0. That means their single pole cannot be exist. So this states that isolated magnetic pole does not exist. This is also a time-dependent or steady state equation which gives the spatial variation or divergence of magnetic induction. Now Maxwell's third equation. The third equation represents Faraday's laws of electromagnetic induction. And mathematically you can write curl of electric field E equals to opposes the rate of change of magnetic induction with respect to time. And this is the partial derivatives. This is the time dependent equation. And this shows that a time varying magnetic field act as a source of electric field. It relates the spatial variation of the magnetic electric field with time variation of magnetic field. Now Maxwell's fourth equation. This fourth Maxwell's equation represents modified Ampere's or Ampere's law of Maxwell's correction. Mathematically, curl of magnetic field can be represented as mu naught into Z plus um, capital D with respect to time, rate of capital D. So this is a time dependent equation, and this equation shows that a time varying electric field act as a source of magnetic field, and the equation relates the spatial variation of magnetic field with conduction current density and displacement current density. So you have to learn about this four equation, which is very famous equation in magnetic statics. Now Faraday's law of induction, we have already studied about this in our previous slide. So Faraday's laws of induction, a changing, that means time dependent changing magnetic field induced or generates an EMF epsilon or epsilon. The magnitudes of the EMF equals minus the rate of change of the flux. Okay, so this is the actually statement of the Faraday's laws of induction, and here phi b equals to magnetic flux, and electromotive force EMF is equals to epsilon. So this is the main Faraday's laws of induction. Uh, Recall, EMF is not a force, but a source of voltage capacity capable of generating power. The EMF is called motivational EMF to distinguish from the chemical EMF or batteries. Recall, the magnetic flux through a closed surface is zero. That means Gauss law for magnetic field. You must know the magnetic flux through the closed surface is zero. The surface for Faraday's law is open in surface. Open. The surface for Faraday's law is an open surface. So now changing the direction of the EMF around a loop. Uh, Actually, this is the right hand rule. You can apply right hand rule for finding the direction of EMF. Now, what will be the Lenz's law? This is very important law. The induced EMF tends to induce a current in the time direction that opposes the changes in magnetic flux. That means epsilon equals to minus d pi b by t. That means negative sign in Faraday's law is more of a reminder, but in Lenz's law, it's just another way to express Faraday's law. So moreover, it can be deduced from it. That means there is a similarity between Lenz's law and Faraday's law. And in Lenz's law, if we move the magnet closer to the loop, what is the direction of the induced EMF? Thus, the direction of the current in the loop. The magnetic flux is increasing pi b equals to surface integral of magnetic field with the small area dA, and therefore this will be positive for increasing flux. Okay, this will be positive. Now, induced current must we create a magnetic field that fights the change. Now, Lenz's law, for the Lenz's law, the induced current must be created magnetic field B that is fight the change. That means this will be increasing. Okay, an induced field, magnetic field down through the loop will create a slight decrease. Okay, thus we have determined the direction of the induced current and EMF. So the Lenz's law, the magnetic flux phi b up the through the loop is increasing, and the fight of the change and induced magnetic field is made that decreases the flux up through the loop. This is the accomplished by the induced current. Induced current, and this is the direction. So Lenz law in summary we can represent like this. This is a frequently asked question for you. If you get time, please go through this question. Now there is a little bit difference between generator and motor. In generator converts the chemical energy, mechanical energy into the electrical energy, but in motor converts the electrical energy into the mechanical energy. A crank or otherwise the mechanically turns a wire loop in an external uh, magnetic field B. This induces an electric current in the loop. But for motor, battery creates a current in a loop. This interacts with an external magnetic field. Here, external magnetic field also to create a mechanical torque. Here, for motor, there will create a mechanical torque. In summary, the Maxwell's equations are these four equations. One is Gauss law for electric field, second one Gauss law for magnetic field, and Ampere's law and Faraday's law. So in short, this is the Maxwell's equation. So you have to remember this. Okay, now I am again discussing the summary of this class. What is magnetic forces? Charged particle experience in electric force when in electric field, regardless of whether they are moving or not moving. So this is another force, and magnetic force. For magnetic induction, this force must be needed. So unit of magnetic field is Tesla. Mm, and for magnetic force, we are given a charge q moving with a velocity b in magnetic field. It is found that there is a force on the charge. This force is proportional to the charge q, proportional to the speed b, and perpendicular to both velocity and the magnetic field, and proportional to the sin pi, where pi is the angle between velocity and the magnetic field. Then this summarizes pi F equals to QB multiply B. So this is the magnetic forces equation. This is the cross product of the velocity vector of the charged particle and magnetic field vector. And we can find out the direction of this force by right hand rule. So we have studied about this. And magnetic force is they are parallel to parallel or anti-parallel. Sin 0 equals to 0 or sin 180 degree equals to 0. And the force is maximum when velocity b and the magnetic magnetic field are perpendicular to each other. So the maximum, and for parallel or anti-parallel, minimum. This force will be minimum. The force on a negative charge is in the opposite direction. You have to remember this. This is the frequently asked question. You must know about this one, and this is also an example. Motion due to a magnetic force. We have also calculated this. And this is the angular velocity speed omega b equals by r linear velocity divided by r. Motion due to a magnetic force, we have calculated this, and for electric force F equals to QE, and magnetic force this. So total force will be given by Lorentz force. Okay, and magnetic force on a current carrying where we have so far that F equals to N Q BD LB, but we must know that J equals to N Q BD and I equals to J A. Then we get another relationship between the perpendicular to each other. Full relationship is F equals to ILB, where direction L is the direction of the current. Now, current loop in a magnetic field, suppose that instead of a current element, we have a closed loop in a magnetic field. So, this is the current loop in a magnetic field. Same. Now, what is the magnetic moment? We define magnetic moment to be mu equals to IA. It is also a vector whose direction is given by the direction of the area of the loop. Okay, we can measure the moments mu this way. Right hand rule using. So this the direction of the area is defined by the sense of the current. We can now write the torque as tau equals to mu cross product with the magnetic field. And this is the frequently asked example and question connecting to this. Now, what is the Hall effect? There is another effect that occurs when we are carrying a current is immersed in a magnetic field. Assume that it is the positive charge that are in motion. So these positive charges will experience a force that will cause them to also move in the direction of the force towards the edge of the conductor, leaving an apparent negative charge at the opposites. So Hall effect can be found by the formula Q equals to QBdB. That means E equals to Hall effect E equals to BdB. Since there is an electric field, there is a potential difference across the conductor, which is given by this one equals to EED. So Hall effect depends on this statement. So the charge carries are the fact the negative electrons. So today we have discussed this one, and this is the summary. Ampere's law of forces, Ampere's law of force, and this is the Biot-Savert's law, uh, uh, magnetic flux density, force and Lorentz force. We have proved this one in our previous, and then Biot-Savert's law, and this is the Biot-Savert's law. So, and types of current distribution we have also studied, and Ampere circuits law in the integral form, and Ampere's law and Gauss law. So, application of Ampere's law, this one application we have derived some one, and for isolated magnetic charge, this is a vector magnetic potential, vector magnetic potential. So, and divergence of magnetic field is zero. This is the Gauss law for magnetic field, and magnetic flux also. We have discussed about this magnetic flux and fundamental laws of magnetostatics in integral form, Ampere's law, Gauss law for magnetic field, and constitutive relation, and Maxwell's law. Four types of law combinedly called Maxwell's law. So fundamentals law of magnetostatics, and this is the boundary conditions for that. So thanks to everybody. Bye for today. Best wishes for. And we have also discussed discussed the magnetic flux, and this is the equation for, and Faraday's laws of induction and Lenz's law. Okay, and induction of EMF, and this is the frequently asked example. So thanks to everybody. Bye for today. There's some most important example for, of example by using Biot-Savert's law. What is the magnetic field 10 centimeter away from a long wire carrying current of 10 ampere? So we have proved that for a long wire, the magnetic field B equals to mu naught I divided by twice pi A. Okay, just putting the 10 ampere, I equals to 10 ampere, and distance is 10 meter. Okay, This is why we get 0.2 Gauss. Similarly, find the force between two parallel wires 100 centimeter long, 2 centimeter apart, and carrying current of 20 ampere. So similarly, the application of Biot-Savert's law for two parallel wires, we get B equals to mu naught I1 I2 divided by L 2 pi pi A. This is the force between two parallel wires. Just putting the values, we get the result. Similarly, the for two long parallel wires, distance 2d apart, carrying equal opposite current I, find the magnetic field B in the plane of wires at a distance x from the line midway between the wires. So in that case, we can find the magnetic field for the first wire by using the first application mu naught I divided twice by distance d minus x. And for the second one, second point, just point will be d plus x. Okay. So total magnetic field will be B1 plus B2. We get the result. Similarly, this is very most important example. I were carrying current I1. First current I1 equals to 5 ampere is bent into a rectangular loop of side A equals to 10 meter and B equals to 5 centimeter. So a very long state where carrying another current I2 10 ampere lies in the plane. So this is the figure for that. This is the A and this is the B part. So I1 coming from here, and this is the long wire I2, and this is the force F1 and this F2 balance each other. So the distance d equals to 5 centimeter, and we can find out the force. First force will be for the first wire mu naught I1 I2 B divided by twice pi d distance. So second force will be mu naught divided by twice pi I1 I2 B by A plus d, just more than a distance. So subtracting, we get the required force, and just putting the values, we get the result. Similarly, this will be the 6.18 will be homework for you. I hope everybody can do this. Just we have used the formula of Biot-Savert's law. So thanks to everybody. By for today, I have everybody will be benefited. The whole chapter of electromagnetic field and magnetic induction. So we have discussed the whole things of this chapter in a summary way. Thanks to everybody. Bye for today.